Welcome to Cloud on Air, live webinars from Google Cloud. We're hosting webinars like this every Tuesday. I'm Zach Stone, and I'm here to talk to you about supercomputers for machine learning called Cloud TPUs. You can ask questions at any time on the platform, and we have Googlers on standby to answer them. Let's get started. Here's a sneak peek at 3 generations of our tensor processing unit systems, or TPUs, that we're going to be talking about today. But before we get into the details, I'd just like to set a little bit of context about the tremendous amount of progress in machine learning there's been over the past several years to explain why these TPUs are so useful. There's a website called arXiv where people are publishing papers in machine learning out in the open. And what you can see here is a plot of the number of papers published over time. The amazing thing is this rate is tracking faster than Moore's law, and we're now up to more than 50 machine learning papers published every day. There's a tremendous amount of activity in the field. And among those many papers, there have been tremendous improvements in accuracy on standard benchmarks, such as the ImageNet image recognition competition. You can see here off to the left, the AlexNet paper that was the first one to apply these deep convolutional neural networks with GPUs to the ImageNet challenge. And then since then, there's been tremendous innovation, both in the network architectures, the systems to train these models, all the way up and to the right here in 2017, and we've even exceeded these accuracies now. But this isn't just about benchmarks for scientific computing. These new deep learning models have also brought about breakthroughs in real-world applications, such as you can see here in diabetic retinopathy. So researchers at the medical brain team here at Google have been trying to diagnose a leading cause of blindness from taking these images of the back of the eye. And they discovered in the process of doing so that you can also get early indications of heart disease in this entirely passive way. This wasn't previously known. And this is just one small indication of how these machine learning models are opening up new applications in medicine and elsewhere that are really going to improve people's lives. Similarly, here, folks have been repurposing old cell phones as listening devices in the rainforest to help catch signs of illegal logging in the central Amazon. So these applications are just a sample of many, many new ways that machine learning can be applied now that we're reaching these high level of accuracies across many different domains, ranging from image recognition to speech recognition to machine translation and more. And one thing that I've found especially exciting is that the same kinds of mathematical techniques are now used to achieve state-of-the-art results across these many different disciplines. When I was in grad school in computer vision, the techniques that we used in computer vision didn't relate at all to the techniques that were being used for state-of-the-art speech recognition at the time, or state-of-the-art machine translation. Now, even though the models aren't necessarily the same, we're finding that they're built of the same building blocks. The dense linear algebra, the matrix multiplies and vector operations that have been put together in this field called deep learning. And so what that means is you can use some of the same tools and the same hardware platforms to solve many different problems. However, there's a challenge. As you can see here, going back to that case study of image recognition accuracy improving over time, as you're getting to higher and higher levels of accuracy, you're also requiring more and more computation. In this case, on the x-axis, you're seeing the number of multiply-add operations, which is sort of a rough measure of complexity of the amount of compute required to run one of these models. But that also corresponds to the amount of compute that you require to train the model. And so we're continuing to move up and to the right, but we're requiring more computation to do it, both to train the model and then to run that model and make it useful. So how do we address this challenge? Well, we believe that the answer is specialized hardware for machine learning, such as these tensor processing units. Here's a brief tour of the history of TPUs at Google. This is the first one that we built that's been deployed in data centers since 2015. This one was focused on inference, and you interacted with one of these whenever you ran a search. It would be used to re-rank the last several hundred results to choose those 10 blue links that you get every time you search on Google. It was used in Street View, in Google Photos, in speech recognition, and across a wide variety of applications that you interact with every day. But that wasn't enough. We moved on after that to the second generation tensor processing unit, which was built into these whole systems. Here, you can see a device that we call the Cloud TPU that you can rent today on Google Cloud. It's in beta, there's no waiting, no sign up. You just follow the link g.co/cloudtpu and fire up a Cloud TPU following our quick start. But these devices aren't just standalone the way the first TPU was. They're actually designed to be connected together into these giant supercomputers called TPU pods. And these will be coming to cloud later this year, both in the larger configurations and in smaller slices that you can use on demand. And the nice thing about the TPU pod is you can apply even more computation to a single machine learning problem to train a model to the accuracy that you desire faster. That helps you really improve your iteration time, because training a model is sort of like compiling code in the world that you're used to of programming line by line. You have to do it over and over again to develop a good application. And at Google I/O, we revealed that we're not just stopping at TPU v2, we have a TPU v3, which is a whole new chip built into these whole new systems that are even larger and more powerful than the TPU v2 device and pod. So just to give you a quantitative sense of how fast this field is moving and the lengths we're going to achieve even greater amounts of machine learning performance, you can see that TPU v1 was able to do 92 teraops, whereas Cloud TPU took that to 180 teraflops, with 64 gigabytes of high bandwidth memory per board, going from inference only in the first generation to supporting training and inference in the second generation. You stitch all those together and you can do even more than 11.5 petaflops with 4 terabytes of HBM. And now the third generation pod breaks the barrier of 100 petaflops, more than 8x the performance of a TPU v2 pod through both a new chip and this larger scale system. So we're really committed to expanding the AI frontier and to sharing our hardware platforms and the software we run on top of them, like TensorFlow, with all of you through Google Cloud. So I'd like to focus on real-world performance with the Cloud TPUs that you can rent today. Now, I know that one thing, if you're training machine learning models or running machine learning models, performance is one of the most important features for you. And I just want to emphasize how important it is to measure performance carefully. We try to emphasize performance measurements that are involving real data, where you have a real model that's training to a specific accuracy, and then you're measuring the complete time to accuracy or cost to accuracy. If you read about performance out on the internet, you might see people talking about images per second or steps per second, and that's important, but it's not useful if you're just measuring that in isolation, because it's really important to make sure that the model that you're measuring that's processing, let's say, lots of images per second, will actually get to the destination you want to go, which is a specific accuracy on a specific benchmark data set. So whenever you're looking at benchmarks, we really encourage you to look for real-world data, not just synthetic data, for time to accuracy, and also look for total cost, especially via public clouds, where it's easy to do these apples-to-apples comparisons. We've also put a lot of emphasis on making our machine learning benchmarks reproducible via open source. So you don't just have to believe the numbers that I'm sharing today. You can run our open source code on Cloud TPUs and measure results yourself, either on standard benchmarks or then on your own data. One benchmark competition that we think was especially well designed was from Stanford. It's called DawnBench, and there's a URL here. This competition recently concluded, and they looked at a variety of data sets, including the standard ImageNet benchmark for image recognition, and they measured both training time and total cost, and they also had other competitions for inference. And we think that these metrics were really getting at the kinds of things that you as practitioners care about in your day-to-day work. I'm happy to announce that we had the #1 DawnBench entry for ImageNet training cost. And we achieved that with this AmoebaNet D model. And the interesting thing about AmoebaNet D is the architecture was actually built on a TPU through an evolutionary process automatically. So instead of designing this model by hand with countless grad student hours, the way most of those models that I referenced earlier have been designed, we ran a search process, measuring a population of models and choosing the ones that performed best on similar image recognition tasks. Then we've open sourced that final winning model, AmoebaNet D, and you can run it yourself on the Cloud TPU platform today. Turns out it trains to the target accuracy of 93%, top 5 on ImageNet, in just 7.5 hours for under $50, which we think makes these kinds of state-of-the-art machine learning results much more affordable for everybody. There's also a model called ResNet 50 that's often used as a benchmark to compare different systems one to the other. And so I should just mention here that our ResNet 50 implementation, which is also open source, is able to deliver 3250 images a second with real data, which is really exciting, and trained to the similar final accuracy of 93%, top 5, which is not easy to achieve with ResNet 50 model. That happens in 8.9 hours for $60. And if you want to go even faster, this is the advantage of being able to scale up into these pods. Here you can see our #1 Dawnbench entry with half of a TPU pod, where we were able to train in just 30 minutes. And actually, if you eliminate the overhead of checkpointing to measure your accuracy at every step, the minimum time is just 23.9 minutes to get to that same 93% accuracy target. So I'm really excited about the fact that you can develop on one of these Cloud TPUs, and then soon you'll be able to scale up with no code changes, just changing your batch size, onto larger and larger slices of these TPU pods. Now, I mentioned earlier the number of archive papers that are getting published every day, and there's real progress happening there, including new tricks that sometimes make it, that change the algorithms and make it possible to achieve your goals even faster. One set of those tricks came from an organization called FastAI, which published a very strong third-place entry in the Dawnbench competition. They showed that if you progressively scale up the size of your training images while you're training, that can let you go even faster in the early stages of your training process. And they also came up with a different, more aggressive learning rate schedule that wasn't widely known, that had been published previously. And they put these together, and they were able to train the ResNet 50 model with this modified training protocol to 93% accuracy much faster. Fortunately, because all this is happening out in the open, we were able to reproduce these algorithmic changes quickly on Cloud TPU after the Dawnbench competition is closed, and that takes our training costs down from $59 to just $25, even at on-demand pricing. So we think it's really fantastic that so many people are out there experimenting with different things, and that they're sharing their results in the open so that you can benefit from them immediately on Cloud TPUs or other platforms. Now, you might wonder, well, what's the next benchmark challenge now that Dawnbench is over? We recommend MLPerf, which you can find at mlperf.org. There's a number of organizations that are coming together to define an even newer and more challenging and diverse set of benchmarks. And so this has been announced recently, and there will be deadlines later this year. If you want to submit your own entries, I'd highly encourage you to do so. So, as I mentioned before, if you want to experience the kind of performance I'm talking about today on these Cloud TPU devices, 180 teraflops, you can do so by visiting the simplest link is g.co/cloudtpu, but you can also follow these other two links to see our documentation, where we have tutorials for many of the models that I'll mention, or you can just go straight to GitHub and read the code yourself for some of the state-of-the-art models that I mentioned earlier today. Now, what's it like to actually use these Cloud TPUs? I want to give you more of a sense of how these things work and what it's like to work with them. So, one important point is that Cloud TPUs are network attached. So this is different from other accelerators. You can choose a VM of whatever size or shape that you want, which I'm showing here in the middle here. The customer, off to the left, is SSH'd into that VM. You can install whatever software you want. You can attach other accelerators if you want to. You can choose a custom size and shape. And then you install our machine image that we provide, which has open source TensorFlow on it with TensorFlow 1.8. And then this VM communicates over the network with a Cloud TPU. Now, this does add one layer of interaction, but we still try to provide maximum flexibility and control with this Cloud TPU infrastructure. And the nice thing about this network separation is that Cloud TPU can either be a single device, like I was showing you earlier, or it could be a whole slice of a pod. You don't have to worry about it. There are no drivers to install, and you can use your VM, which can be small, to drive this enormous supercomputer to get your training jobs done quickly and efficiently. Now, as I've mentioned throughout, these Cloud TPUs today are programmed with TensorFlow, and I'd recommend using TensorFlow 1.8 to get our greatest optimizations and the maximum performance that we're able to deliver on Cloud TPUs. Now, TensorFlow is a really practical and popular toolkit. Ever since being open sourced in November 2015, it's just really taken off. If you look at these GitHub stars, they're just up and to the right. I think this is now within the top 5 most popular projects on GitHub overall. And we've seen more than 13 million downloads of TensorFlow all around the world. So this is really a production-ready framework that's used in everything from research labs to applications that you interact with that have billions of users. Now, TensorFlow is a whole ecosystem, and I'm going to focus today on the TF Data API, on layers, estimators, and XLA, because those are the components that you use to program these Cloud TPUs. So estimators and layers are these high-level deep learning abstractions for TensorFlow that you don't just have to use on TPUs, you can use them on other platforms as well, and we're trying to make it easy for you to shift code back and forth from one platform to another, so you're not locked in. Now here's an example of the kind of model you might write with layers and estimators. This is a convolutional model. And so you can run this on your local computer. And how do you change it to make it compatible with a TPU? Well, in this case, you just have some small changes to make. You wrap the optimizer here, as you can see, and then you're using a TPU estimator. And we're working to minimize these changes over time. Now, one thing I want to say, though, is that high-performance computing is challenging on any platform. And so we've put a lot of effort into building a set of reference models that are open source that you can just use right away as starting points, so you don't have to do this performance optimization from scratch yourself in these many different application domains. So to give you a sense of the reference models, a snapshot that we have today, we've got the kinds of image recognition models that I've already discussed off to the left, including this state-of-the-art AmoebaNet model. We've also got various sizes of ResNets and inception models of V2, V3, and V4. But we've also got object detection with RetinaNet that helps you find multiple objects in an image. We've got low resource models like MobileNet if you want to then deploy your model out at the edge on a phone or a vehicle or some other device. But these TPUs aren't just limited to image recognition and object detection. They're also useful for machine translation or language modeling, or even sentiment analysis or question answering. I'll say a little bit more about that in a moment. And beyond language and text, we are seeing emerging applications on these TPUs in speech recognition, which you can find in the Tensor to Tensor toolkit. I'll say a bit more about that. And if you're more of a researcher, you're interested in generating images from scratch and some of these far out applications where these machine learning models are synthesizing new types of imagery and sound, you can do those on TPU too. And we've got a great example of an image transformer model. So let me go through some of these applications and this variety of applications in turn. So image classification, typically you're focusing on small crops of images like you're seeing here, and then applying a category. This is useful for everything from photo sharing to medical imaging. Object detection, like I mentioned before, you might have a larger image like I'm showing here off to the right, and you want to detect a bunch of items in it and classify them and apply labels with different confidences. In this case, RetinaNet can operate on surprisingly large images, 896 by 896, achieve a near state-of-the-art result on COCO, a standard object recognition data set, and you can get to that level of accuracy in about 6 hours for just $40 on one of the Cloud TPUs that you can rent today. I think that's pretty exciting for democratizing machine learning and providing a building block for you to build your own object detection applications on top of. In machine translation, on the WMT dataset that translates English to German, we get to a blue score of 28.6 in just over 6 hours, again, for around $40. For language modeling, as you might use for an application like Smart Reply, where you're trying to predict what words or phrases happen next, it costs a little bit more because you have to train longer to get to the state of the art, but you reach the state of the art in just 74 hours, again, for under $500. And this, for the latest hyperparameters, I'd recommend following the short link on screen now. That takes you to the Tensor to Tensor toolkit, which is built on top of TensorFlow and is moving even faster and really keeping up with or extending the state of the art in research. For speech recognition, which you can also find in Tensor to Tensor, you can get to a word error rate of 7.9 in just 13 hours for $86, or you can train longer to get even closer to the state of the art with a 7.3% word error rate. And this is a really great starting point for processing large volumes of audio, or training your robot to listen to your voice commands, or anything else you'd like to do. I'd also like to emphasize that even techniques that you wouldn't necessarily think are a good fit for accelerators, like question answering, can be accelerated. Here's a QANet where you take in a paragraph of text, some region of unstructured text, and you're asked a question that has an answer in that text. And this QANet will highlight the fact in this unstructured blob of text that corresponds to the answer. This is a fast implementation that won the Dawnbench Squad Challenge. And so there's going to be an open source implementation of this coming soon. Now, I mentioned image generation earlier. You can see off to the right in these rows of different categories, these images have actually been synthesized from scratch using the image transformer model. And using a Cloud TPU, you can get to a score of 2.98 bits per dimension, lower is better in this case, in 30 hours for under $200. I've also provided a link to the paper here if you're interested in learning more. So I've mentioned this variety of reference models, and there are more coming all the time. I'd really encourage you, even though it's tempting, to take some older code and try and port it to the TPU. I'd really recommend starting with one of these reference models to experience the full performance of the platform right away, and maybe even reach higher accuracies since these models are so close to the state of the art. They're high performance, they're open source, they're cutting edge. We continuously test them for performance and accuracy, even as all the versions of underlying software are evolving rapidly. And they really let you get up and running quickly. And then it's your code, it's open source, you can modify it as you need and train and run on your own data. So I want to emphasize, though, that you don't just have to use these reference models. You can build models from scratch using layers and estimators and the TF Data API. And there's lots of detailed technical advice in this troubleshooting guide and also in our performance guide and our documentation about tools. But we're really trying to do the hardest work for you via our reference models. So definitely start there today. Just to give you one quick sense of why high-performance computing can be so hard, when you're using previous accelerators that may not have been as fast, it's easy to overlap your input processing with your training. And so then you're fully utilizing your accelerators, which are often the most expensive part of the system. But now, when the accelerators get faster, suddenly you're bottlenecked on the input processing and your accelerators are idle, waiting for data. It's quite challenging to build these balanced systems that can keep the fastest accelerators supplied with data all the time. And so that's really what we're trying to do with our TPU supercomputers and also with all these software layers that we build on top. Fortunately, if you are performance tuning one of these models, we've got these great tools that are integrated with TensorBoard and available for Cloud TPUs. The Cloud TPU profiler lets you actually get detailed op-by-op statistics about how your models are performing and where they're bottlenecked. And this is a really amazing tool to let you optimize your own models and get them running, training at full potential. We even try to give you high-level advice. I don't know if you can read it here in red, but this is telling you that your program is not input-bounded, so keep working on your step time. We're really trying to provide higher and higher level guidance as you're optimizing these models on the TPU. So let me just say for a moment, why we recommend doing machine learning in the cloud, how that's providing advantages to you, even if you're used to working under your desk or in an on-premise data center. Google Cloud provides top-notch infrastructure, and you can mix and match whatever components that you need. You can provision quickly, you can scale up, and then you can scale back down as your needs change and really burst to take advantage of teraflops or even petaflops of machine learning compute. We've also got a variety of different accelerators. We've got the best of CPUs, GPUs, TPUs. You can mix and match those together to get the right mix for each workload that's interesting to you. We've got fantastic security, world-class security, and powerful tools for data access control and controlling the way that it's being used. And most importantly, we let you reduce your capital expenditure. Instead of having to place orders for hardware, wait for months, deploy them, change the cooling and power in your data centers to support these powerful accelerators, you can just use our on-demand pricing to pay only for what you need. which we find to be much more economical, especially when your workloads are unpredictable. Just to give you two examples of customers who are using Cloud TPUs today, both 2 Sigma and Lyft have found it really convenient to be able to move to the cloud, take models that they already had in some cases and accelerate them, or take our reference models and use them to achieve new results on their own internal data sets. Now, I'll give you just a brief glimpse under the hood to give you a little bit more detail on how these Cloud TPUs are able to achieve such amazing performance. Now, I mentioned before that each Cloud TPU delivers 180 teraflops of computation with 64 gigabytes of memory, and it's actually got 4 chips, one under each of those heat sinks. And so here, in just a minute, I'm going to focus on one of those chips. But first, let me explain that the Cloud TPU is connected to a host behind the scenes via PCI. So you get the benefit of both this host, where some operations can be placed, and then ideally as much of the computation as possible is placed on the accelerator. So let's zoom in on one of these TPUs. So the Cloud TPU chip is divided into 2 cores, as you can see here. The chip as a whole has 16 gigabytes of HBM split between the cores. And each core delivers 22.5 teraflops and consists of a scalar unit, a vector unit, and especially this matrix unit, which is really special and uniquely suited for the demands of high-performance machine learning. Now, focusing on this matrix unit, it's actually a 128 by 128 systolic array. Now, systolic arrays are this old idea in chip architecture, but they're newly relevant now that we have these deep learning models that have many, many layers and consist of many matrix operations, often on these gigantic matrices. One important fact about our matrix unit is that we're actually using a different floating point format, bfloat16, in the multiplies, even though we're doing float32 accumulate. And that turns out to be a great floating point format for machine learning. It's almost a drop-in replacement for float32, and yet it lets us pack even more compute into the same amount of silicon area. So let me tell you just a little bit more about bfloat16. So you may be used to programming in float32. That's what most people use today for machine learning models. And here's how those 32 bits are distributed between the exponent and the mantissa. Now, IEEE float16 chops both of those down, so you have a much reduced exponent and a much reduced mantissa. bfloat16, by contrast, actually uses a lot more bits for the exponent, which lets us represent numbers that still have this full range, but you lose a little bit of detail in fine distinctions between numbers. Turns out for all of these state-of-the-art deep learning models, those fine distinctions don't matter, but the range matters a lot. And so you get a much simpler user experience working with bfloat16 than you do having to worry about FP16, where you've got to think carefully about whether the numbers are in the right ranges everywhere throughout your model. And there are complicated techniques that you have to apply on a model-by-model basis to avoid your numbers exploding or underflowing or all sorts of numerical problems. We reduce those problems a lot by working with bfloat16 on the Cloud TPU. So now here, I just want to show you a 3x3 toy example to represent this 128 by 128 systolic array to give you a sense of how, as input data is streaming through, there can be a lot of reuse of intermediate computations inside the systolic array, which gives this fantastic throughput for these large matrix operations. Now, I just want to look ahead briefly to give you a sense of where we think the field is going and why these Cloud TPUs and TPU pods are so well suited to help support the future of machine learning products and research. Now, these Cloud TPU pods enable you to train with very large batch sizes, which you might wonder, well, how does the scaling go, as you go beyond a single device? Fortunately, we've got this proprietary network that connects all these devices together in this mesh, and we've been able to show near perfect linear scaling out all the way to the full-scale pod, as you can see here as the number of devices increases to 64, which is the full set in the TPU v2 pod. Now, I mentioned large batches. One other issue you have to wonder about when you're dealing with large batch training is whether you can still make efficient progress towards the ultimate goal. Previously, as people increased the batch size, at some point you would find that you wouldn't reach the final accuracy that you were expecting. And so there was sort of a mathematical limit in how large you could make the batch size before it was no longer efficient or useful to do so. But there's been a lot of progress on this recently, and there's still very active research. And what I'm showing here is that a model that might take, in that sort of golden curve, many hours on a single board to get to this 76% accuracy, as you scale up within the pod, just increasing the batch size, not changing the code, you can achieve that same accuracy in shorter and shorter wall clock times, which really lets you iterate faster. Because remember, this is like compiling your code, right? You need to compile your code many times to iterate and explore. And sometimes if you're doing something like hyperparameter tuning or neural architecture search, you want to train hundreds or even thousands of different models. And on these pods, you can really pull that time in to get to the same accuracy and iterate much more quickly and make faster progress. Now, here's just a glimpse of our future roadmap. I mentioned the TPU v3 pod that we announced at Google I/O. And here's the full system with these 8 racks. And the whole pod, as I mentioned, is more than 8 times more powerful than the TPU pod. And actually, to get to this level of performance, we brought liquid cooling into our data centers for the first time, as you can see here on one of the boards that makes up that gigantic TPU v3 pod. So we're really excited about continuing to expand the frontier of machine learning. You can get started with Cloud TPUs today. There's no waiting, there's no sign up, there's no need to make a quota request. Every GCP project can start a Cloud TPU today. And you can follow just the link at the bottom, the g.co/Cloud TPU link to get started, or one of these other links to peruse the code of our open source reference models, or jump straight to our documentation. With that, I'd like to invite you to stay tuned for live Q&A. We'll be back in less than a minute. Hi everyone, I'm back to answer your questions about Cloud TPUs. So one question here is, I filed a quota request and haven't heard back yet. When will I get a chance to try Cloud TPUs? The good news is, as of recently, you no longer need to file a quota request. Cloud TPU quota is available to everyone. So you can just go to Google Cloud today, and you should find quota for at least 2 Cloud TPUs, possibly more, and you can start one up right now in the US Central region. Let's see, there's another question here asking about the performance of TPUs versus GPUs or other platforms. Now, as I mentioned earlier, one thing that we really recommend is that you perform your own benchmark measurements on the workloads that matter to you, using ideally our reference models that give you this great starting point. But in any case, we really emphasize that you should benchmark with realistic training data. So you're measuring the actual accuracy along the way, not just the samples per second. And think about the total time that it takes to get to an accuracy if you're measuring training, or the throughput if you're measuring inference, and also the total cost on public clouds. Or if you're working on premise, the whole CapEx and OpEx to run the machines and maintain them, to get a complete picture of how to compare one platform to another. If you want to look at TPUs and GPUs specifically, one of our customers, RiseML, has published a series of blog posts where they've looked at TPU and GPU performance quite carefully. You can also look at the Stanford Dawn Bench results. Let's see. where can I access these reference models? So in the TensorFlow GitHub repository at github.com/TensorFlow, there's a directory /TPU. And a lot of our reference models are in there. As I mentioned during the talk, though, there are some of these that are also in a different repository, which is called tensor2tensor, where the 2 is a numeral, and it's all one word. And so keep an eye on our reference repository in GitHub, and then also take a look at the tensor2tensor library for the real cutting edge of these sequence-to-sequence models. This is a great question. Can I do inference on TPUs or only training? TPUs support both training and inference. At the moment, our software stack is continuing to mature, and I'd really recommend training and batch inference. Over time, as we continue to optimize the software stack, TPUs should be great for low latency inference too, but I would wait just a little bit longer before diving into that. And now somebody's asked, well, wait, this is the second generation of TPUs. Is there a third generation? And so, as I mentioned through the talk, we revealed the third generation TPU at Google I/O. It's liquid cooled. We assemble them. It's a whole new chip and a whole new system that we assemble into much larger pods that deliver more than 100 petaflops of compute collectively. So we're pushing the frontier forward as far as we can to enable us to train even larger and more powerful and accurate machine learning models that will then, benefit all the users of Google products through all our different applications. Let's see if there are any other questions here. Great. So one other thing that you might wonder about is how to do sort of interactive development with these cloud TPUs. And one thing that I'd recommend would be, do as much as you can with layers and estimators and the datasets API on a cloud TPU before you think about scaling up into a slice of a pod. So the experience that we're really trying to build towards is one where you can, inexpensively treat one of these cloud TPUs as your personal supercomputer in the cloud that you can just sit on. Instead of having to worry about a machine under your desk, you just log into the cloud and pay only for what you're using as you do your development. And then when you're really ready to scale up, just by changing the batch size, suddenly you're able to transform, days into hours or hours into minutes and get a lot more done in a day than you used to be able to do in a week. So we're building a whole new paradigm for machine learning, research, development, and production here with Cloud TPUs. And we invite all of you to join us on this journey and try out Cloud TPUs today. Thanks very much. Stay tuned for the next session, which is make your applications fast and reliable with the Stack Driver API. Thanks again.